Boom! All right, folks, Hume again. So we continue our discussion of vectors, and as I promised in the last video, in this video we're going to go a little further in terms of the vectors that we use for the purposes of example, just to illustrate the point that the vector could go anywhere. So for the purpose of simplicity, we use vectors, well, in the case of this particular vector, right? We would recall that this vector, let me call this the vector A, right? So we're going back to the naming conventions now. This was the position vector A, and we said that A was equal to 6, 8, right? And we said that A was also equal to 6i plus 8j. Two different ways of writing the same thing. Again, the line underneath signifying that it is a position vector originating from the origin. Look at this vector. Same orientation, but different direction. So this vector, in other words, that is the vector OP, right? Yet another way of denoting the vector. So OP with the arrow means that we're starting from O and we're going to P. The position vector will always start from O. So any position vector will always have O as the first letter, followed by the letter where the vector ended up. So in this case, we start from the origin O and we end up at P. Let me say we go in. Let me say this is the point Q. Right? This is the point Q. So again, this vector, same orientation. For the purposes of coordinate geometry, same line, same gradient, but the direction is different. In this case, the direction is up like that. In this case, the direction is down. So again, we're making clear the difference between orientation or gradients and direction, where vectors are concerned. So in this case, we start, remember, that we're going with the horizontal first, followed by the vertical. So in this case, your horizontal movement is to the left, which would be negative. So 1, 2, 3, 4, 5, 6, minus 6 to the left, and then it will be minus 8 down, right? 1, 2, 3, 4, 5, 6, 7, 8. Of course, it is not drawn to scale, so don't expect any exactitude here. So saying that it is a position vector and the movement is minus 6, minus 8, then we will end up at the point minus 6, minus 8, because the position vector will always end up. The movement denoted by the position vector will also indicate the coordinates where the vector ends, where the point ends up. Right? So in other words, if we say, let me say this is the vector P. Let me make the letters coordinate a little bit now, man. P, right? That's the vector P. Let me say this is the vector Q. Position vector Q is equal to minus 6, minus 8, which in, I forget the name for this notation. This is the vector notation. No, maybe this is the matrix notation, and this is the vector notation. This will be minus 6i minus 8j. Right? So you're getting the exposure to the different ways of writing it, and you're actually seeing the negative signs enter in the picture now. And of course, in this case, your OQ is equal to, well, your OQ is equal to minus 6, minus 8. So in other words, your OQ is the same as position vector Q, which is equal to this. Right? In this case, your OP is still the same, 6, 8. All right? So you're seeing three different ways of denoting a vector. You could write it as 6, 8, where you write it either as OP or position vector P. You choose some letter. You choose some letter here. Or you go into the exact coordinates now, where you're dealing with the components now. So in other words, the I denotes the horizontal component of the movement, and the J denotes the vertical component of the movement. So you have here the precise components of the movement, 6i plus 8j. So in other words, the direction of OP is 6I plus 8J, right? The direction of OP is equal to 6I plus 8J. The direction of OQ is is minus 6I minus 8J. And if you notice, minus 6I minus 8J is exactly equal to minus into 6I plus 8J. So in other words, by simply putting a minus sign in front of this, we have reversed the direction to give a new vector. But mathematically speaking, this new vector is simply the negative, or sometimes I like to use big words. Sometimes I do like to use big words. But I will indulge myself for 5 minutes here. This vector here is what I would call, and watch the language now, maybe I could call it the directional reciprocal. Woo, that sounds good, eh? The directional reciprocal, right? Reciprocal. Or maybe we could even refer to it as the vector reciprocal, whatever. Right? You don't want to try to remember that. That's just me playing the fool a little bit. The whole idea is that direction is reversed. That is all. Alright? Nice. So we deal with that. Let me deal with the other two fellas now. OP, let me say OP PQR. So let me say that this guy here is the point R. Alright? This is the point R. And again, the movement is 6 to the left. That's the initial horizontal movement, followed by 8 up. Alright? Again, because this is a position vector, this will end you up at the point minus 6, comma 8. Right? In other words, all we're saying here is that the position vector R with a line under it is equal to 6, 8. The R is also equal to, not 6, but minus 6. Let me do this over. Come. So yeah, R with the line underneath it is minus 6, 8, which is the same thing as minus 6I plus 8J. And of course, your OR, the direction OR is given by minus 6, 8. Alright? We come down here now. PQRS. So this is the point S. This is the point S. In this case, the horizontal movement, the horizontal component of the movement, the horizontal component of the vector OS is 6 across, and then the vertical component is 8 down. So that will end us up at the point 6, comma, minus 8, because it is a position vector. And just as we did in all the other cases, the position vector S with the line underneath it is 6 minus 8, right? Which is the same thing as 6I minus 8J. So that's, hold on. Yeah, 6I. Best we leave the original 6, boy. Ja. That looking more like a B. 6I. Yeah, that look more 6-ish. Minus 8J. Or we could say that OS is equal to 6 minus 8. Right? Nah, whatever. 6 on top, minus 8 below. You get the point. Alright? So, the whole point is that a vector could point in any direction. There is no special rule that says the vector has to be looking nice and cute in this first quadrant here, and have to be pointing in this direction. And just as we had a parallel vector of the same magnitude, the same length, same direction, we could have the same for all of these other vectors as well. Right? And just as you would use your Pythagoras theorem to find the length of this, as we would have discussed in the videos on coordinate geometry, you could also determine the magnitude of the length, the length of the vector, which will be an indication of the magnitude by using Pythagoras theorem on the components. And what you will find is that in each of these cases, regardless of the relative directions, the magnitude is always positive because the magnitude is just referring to the length of the vector. Right? So whether we have, hold on. First of all, I might just do the same thing here that I did for the others. Right? So O, we would PQR. Right? So OR is equal to minus 6i plus 8j, and OS is equal to 6i minus 8j. Of course, you realize that 6i minus 8j is the same thing as minus 6i plus 8j. So in other words, OS is equal to minus OR, and OS is the same thing as RO. So in other words, if we start from R and we move towards O, we're traveling in the same direction as if we had started from O and we move to S. So in other words, RO is in the same direction as OS. Right? Remembering, however, that OR is negative of OS. Right? Remember, of course, that the negative sign means that we're reversing direction. And it's the same thing with OP and OQ. Right? Your OP is negative OQ, which is the same thing as QO. Alright? So Q to O is in the same direction as O to P. Remembering, of course, that O to P is opposite of the direction from O to Q. These are the basics. So by looking at this video, even if you don't catch everything, it will put you in a position where, as we start to do questions, whether you're doing the questions with me, or with a teacher in school, or with your friend, or with the neighbor across the road, you have something in there that you could work with, as opposed to ignoring the videos and going to study questions with nothing in the tank. You can't start questions with nothing in the tank. You have to have something in the tank. Right? You might catch all of it or you might catch some of it, but you have to have something in the tank. And that's what we're doing here with all of this long talk and explanation. So you're here and that is great. Keep it up. Stay in the game. Alright? So by using examples, we'll be talking about certain features, certain characteristics, certain qualities of vectors in general. Alright? And any of these four vectors, any of these four position vectors could be replicated in other parts of the coordinate geometry system. However, just to remind, once the vector does not originate at the origin, it is not a position vector. It is just a displacement vector. It is given the information as to the displacement of a point and the direction of the displacement. Right? So it is the directional component that gives this the quality of being displacement and not distance, because we know what direction it is. If we're talking about position, it means we're referring back to the origin. A slightly different thing. Yeah? So that's it where this video is concerned. This video was just about expanding the examples so you don't fall into the trap of looking for this alone. You could find this, you could find this, and you could find this. And you could find any vector. In fact, any vector that you could possibly look at will generally take one of these four general orientations. Of course, we have the other four where you're going directly along the axis. In other words, if you have a horizontal vector, it means that that vector will be parallel to the x-axis. If it is moving in this direction, it will be opposite to a vector moving in this direction. Right? Same thing with the vertical. If you're moving up, it will be opposite to a vector moving down. Right? Of course, we don't need to do too much explanation because the horizontal and the vertical are actually the reference orientations that give us, know the language now, a frame of reference by which we could denote exactly any vector. So any vector that is not exactly horizontal or vertical will possess some level of diagonality. In other words, it will be diagonal. Right? It might be diagonal, almost flat, diagonal, almost vertical, or somewhere in between, which throws us straight back to the concept of gradients in coordinate geometry. But any diagonal vector can be expressed as the sum of a horizontal vector and a vertical vector. Let me say that again, and that's basically what it is. Any diagonal vector can be expressed as the sum of a horizontal vector and a vertical vector. Remembering, of course, that in this notation, we use the horizontal vector first, and in this notation, we use the horizontal vector on top. If the vector is parallel to the horizontal axis, if the vector is horizontal, then it means that the vertical component is 0. And by the same token, if the vector is parallel to the vertical axis, if the vector is vertical, it means that the horizontal component is 0. Let me say that another way. If the vertical component of a vector is 0, then it means that the vector is horizontal. And on the flip side, if the horizontal component of the vector is 0, it means that the vector is a vertical vector. That's it. Yeah? So, we could end the video here. The next video we will talk about what we refer to as vector addition, where we talk about what we refer to as the parallelogram law and what we refer to as the triangle law. And after that, we will be in a position to start doing questions. Alright? So you put a little gas in the tank and then you start doing questions. Easy questions at first, followed by slightly more difficult questions until you get to the point where no matter how they come, you can deal with them. Alright? One more thing. If two vectors have the same direction, or you see, I remember something here, man. I'm now getting ready to go, and I remember one more thing. If the two vectors have the same direction, or they have the same orientation, meaning that in the language of coordinate geometry, the vector, the gradient is the same, but the direction is opposite. Right? They are parallel. We already discussed that. If, however, two vectors with the same orientation have one point in common, they are what we refer to as being collinear. So, for example, OP goes like this, and OQ goes like this. but both of those vectors have the point O in common. And we already established that OP has the same orientation as OQ, even though the direction is different. It means that having the same point in common, it means that the vectors are what we refer to as collinear. And as the name implies, let me spell it out first. Collinear. I think collinear is 1L. Yeah, right? Collinear. Let me see how the syllabus spell it. Hold on. Parallel vectors, equal vectors, inverse, blah, blah, blah. Blah, 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 blah. Blah, 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 blah. Blah, 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 blah. All right, they mention it explicitly here. Okay. As the name implies, collinear means that the two vectors are on the same line. So again, you see the intersection of vectors and your coordinate geometry. You can't avoid that. That is unavoidable. So even in a case where the directions are opposite, if the direction is opposite, it means that the gradient of the line is the same. It means that the lines are parallel. And if the two parallel lines have a point in common, then they have no choice but to be collinear. Same thing over here. Opposite directions, OR and OS, but they have a point in common. It means that they all lie along the same line. It means that they are collinear. Right? So it could be parallel without being collinear. Bim bam, bim bam. Remembering, of course, that parallel is same direction or opposite direction once the orientation is the same. If the orientation is the same and they have a point in common, then collinear. Yeah? That's it. So I think I could end the video now. Yeah? Right, let me finish before something else pops up again. Right, so stay tuned. We have our next video coming up, and we have more videos coming up as we continue in this series.